recording, and then we'll start.
All right. So
when this pops up. Okay.
Hello. We had Fast Global Solutions for our senior design, where they asked us to develop a test device for an electrical component. I'm Chris Swedzinski.
I'm Steve Taylor.
Tyler Wanzek.
I'm Sam Hampton.
So what we will talk about today, we will explain who Fast is, what they make and their product overview, our project objectives and our deliverables, the different solutions that we looked into, the study data with what they're doing now and what the improvement will do, the cost-benefit analysis of implementing this test device, the SOP for operating the test device, and finally our selected solution. So who is FAST? FAST was founded in 1979 as WASP, or Watkins Aircraft Support Products. But in 2015, they combined with FAST Manufacturing to become Fast Global Solutions. It is an ESOP company, which is 100% employee-owned, with over 700 employees at 8 different facilities. They have 3 different divisions in their company: WASP Ground Support Equipment, or GSE, the one we will be focusing on today, WASP Conveyors, and Fast Ag Solutions. So the products that we will be focusing on is in the ground support equipment are all made for the airlines, airports, and the air cargo industry. They are made to safely load planes, deliver cargo around the airport, all while keeping the cargo secure and safe. So the objectives that FAST wanted, they want us to develop a test device to allow us to test the control panel for the scissor lift that they build. And with this, to be able to minimize the rework time that's caused by it, along with evaluating their current assembly process, making any long-term recommendations on their assembly process, and the ROI and cost-benefit analysis of purchasing, installing, implementing, and building our test station. So the item we will be focusing on from them is their scissor lift. It has a platform area of 88.41 square feet. It's powered by a 24 horsepower Kohler engine that powers 2 hydraulic cylinders to lift the platform up and down to the aircraft cargo doors to load with supplies. It can lift approximately 15,000 pounds, and it has 4 work lights in each corner to be able to operate any time of day. The errors that FAST identified for us that were occurring with this were improper ring connectors that they receive as purchase parts, their dash control panel wiring issues where the assembler would mess up a wiring, get wires crossed, something like that, or as well as improper diode connections.
So this here is the overall electrical schematic of the entire system. Can look very complicated at first, but the only section that we were really portraying to our project was the blue section highlighted with the star, and that's the dash control. Dash control, you can go to the next slide. The dash control is the main focus of the project. We designed this project to be kind of a baseline for other systems. So this system that we designed is does not apply to other systems, but this system can be built relatively simply for other systems. This is the dash control itself. The main functions that it does is it has the starter, and it has the glow plug, which is a preheat for the engine. And this also houses most of the relays that communicate with the rest of the peripherals of the scissor lift. Directly in the center, there's the silver turnstile knob is the ignition key. To the right of that is the glow plug, and then to the right of that is the shutdown switch, which it has to be turned or flipped while you're starting the engine.
All right, so one of our first things we did for our project was do some research on available wire testing methods done in the industry. One here pictured on the left is from SDI in West Fargo, who assemble wire harnesses with various different termination points. So they have a Dynalab tester, which we looked into, which is just continuity testing and point-to-point testing. We were then advised that the functionality of these testing devices wouldn't work with the complexity of our control panel, so we looked to other ways of building a tester. Our first solution was a PLC using ladder logic to program that. We were provided with a Tweedo PLC controller by Fast, so the cost was a lot lower for this option. We would plug in the PLC to the dash and run through the test operations that we need to run a test for the dash. The benefits is the PLC can be reprogrammed and configured to test other control units in the future, which was expressed by Fast as something they would like to do. And they are familiar with the Tweedo PLCs from previous projects of theirs. Another option that was brought to us by an advisor instructor of the electrical engineering department at NDSU, we unfortunately were not able to get more information after spring break and after not being able to go into NDSU's labs and kind of play more with this and see if it was more of a viable option. So we ended up exploring more into the PLC. So here's our solution that we came up with: a portable cart with an extension cord that can be plugged in anywhere and stay out of the way of the assemblers if it's not in use. And then we would fabricate a sheet metal interface panel that would go on the middle part of the cart with our indicator lights and our connectors, the Deutsch connectors. And then on the lower part in the enclosure, we would have a separate enclosure with our PLC, and then grommet holes for all the wiring to travel throughout the cart. So a closer look at the enclosure and the 3 grommet hole locations on the enclosure inside the cart, and then the removable plate inside of the enclosure on the far right with the DIN rail terminal blocks and the PLC. To see further detailed drawings of this, you can see that in the appendix. And then for the interface panel, that's kind of the placement of where that would be. We can further enclose that space if need be. And there's plenty of space on the interface panel to expand for more lights and more connection points. Steve will talk about the electrical schematic now.
Okay, so this is the electrical schematic we came up with. Directly in the center, you can see that the PLC, with all of its the relay ins and DC outs, will be wired to terminal blocks. And the terminal blocks, if you're not familiar with, are on page 8 of the appendix. These terminal blocks will be mounted onto a DIN rail, as will the PLC, and they'll just be a way of organizing the wires and making stuff neat within the enclosure. Then those terminals are wired to our female-ended Deutsch connectors, which are the connectors that are the leads off of the dash control. So the connectors on the dash control, the two 8 and 12 pin connector will plug into the interface and then communicate through the terminal rails into the PLC. How I came up with this electrical schematic. If you look at appendix page 1, there is the dash controls electrical schematic, and what I did was I figured out what is going to be energized after each initial step. So when you turn the key, which wires are going to be powered, and then when you flip the glow switch, what is going to be powered after that, and so on. After I got that, I was able to convert or change which pins are going to be inputs and which pins are going to be outputs, and I was able to then write the ladder logic. The ladder logic, again, if you look at page 3 of the appendix, it has all the notes that which is going where, and then where the associated pins and inputs they are on the dash control and on the tester. Just to kind of go through the motions of what would be going down during this test, you would initially turn the key to the run position, which energizes the dash control, which is followed by the stabilizer light, the temp light and oil light to turn on, in addition to 2 other lights on the indicator panel on the tester. So that signifies that all of those are working. Next, what you do is you operate the glow plug, and the timer, once the timer runs out on the glow plug will turn off, and another light on the indicator panel will turn on. And then finally, you turn it, you hold the shutdown switch, and you turn the ignition to start, and then you release it, and then finally, the 4th light will turn on. Once all 4 lights on the interface panel on the tester turns on, that means that is a fully functional dash control unit that is passed inspection. If not, there in our SOP that we created, we are there's points in the SOP that say if this light does not turn on, check the voltage across these 2 points, or so on. And then we will go to Chris with the bomb.
So this is the BOM that we created in regards to what you will need to build this test device. Unfortunately, because of the current situation, we were not able to build the device, but this is roughly what you will need to be able to assemble, build, and have a working, operating test device for that control panel. Through looking up the components online, we estimate the price will be around $536.25 for the materials. The BOM is a more detailed BOM with where you can purchase these is also available in the appendix.
We had time study data given to us from the company, and from that data, it was determined that the assembly time for the control panel, which is all we needed to focus on, was 10 hours and 38 minutes and 15 seconds. And so when we adjusted the assembly time with the new process that would be added, which is going to be testing the unit to make sure it works, we added 5 minutes because that's what we estimated it would take to use. And that would change the new assembly time to 10.72 hours. And then we didn't worry about material costs, since we're not going to affect that with this project. We're only going to try and shorten time, so the only cost that matters is labor cost. And we adjusted the labor cost based off of the data that we were given, which was that it takes about 1 to 2 people to build one of these. And so we used an average labor cost of $97.50 per hour and multiplied that by the assembly time, which gave us $1,036.43 to build one of these control panels. And then we also calculated the rework which we were given to be anywhere like around 40 or more hours. And so we just did the same thing there, which is multiply the labor cost, because it also takes 1 to 2 people, and multiplied that by 40 hours and came up with at least $3,900, potentially more, for reworking. And that's what we used when we were calculating our cost and benefit analysis, because we know that our test unit is estimated to cost $536, and our current assembly cost was $1,036. And when we added the extra 5 minutes, that increased the assembly cost by about $9. And so when we estimated the amount of time that would be saved by doing this, we didn't really have a means to test it properly, but we guessed that it could save at least half, which is a good amount. And that would cut the average rework cost to $1,950 and save about $1,941 per unit module, per control module. And then, so our machine would pay for itself after one reworked unit. We developed an SOP, or standard operating procedure, for the operators so that they could learn how to use and operate this test device. And you can see a more detailed section of that in the appendix. There's also a section in the SOP about troubleshooting in case they run into any problems. We decided to go with our solution because of the availability and because it's relative ease and low cost, because we had access to a lot of these things. We also picked it because we can keep the design fairly basic and leave a lot of room for expansion if they want to use it for future products and test their other units. The only problems were that the enclosure might not have suitable venting for keep the temperature level. There could be licensing software, like software licensing issues. And due to the circumstances, we weren't able to fully put one together and assemble it, so we couldn't test it.
Conclusion, we showed you who FAST is as a company, what they do. We showed you what they make in their GSE division. We talked about our deliverables that we were assigned and what we delivered to FAST. We talked about the different things we looked in as potential solutions for this project. We showed the time study data from what they currently do to what the improvements of our test device will achieve. We showed the cost benefit with if they implement the unit, it will pay for itself after one use. We touched on the SOP development and how those will, how they have troubleshooting and different, how to use the device correctly and safely. And we described our selected solution. Any questions?
So what are they currently doing now for testing on this unit?
They don't.
They test it after it's built.
So they'll just put it onto the final assembly, and because this is such it's where almost all of the communication goes through. If they put it on there, it's kind of like the bottom of a deck of cards, where they're not certain which one it is, but it's gonna cause a cascade down the rest of it, where none of it's gonna work. So yeah, they just assemble it onto the final assembly and just hope it works. They have been using voltmeters to just check for continuity, but with the logic that goes with it, continuity isn't good enough. So you need some sort of logic that's going through this to test the functions properly.
So they're basically, the test is actually when the whole thing's built and they apply it and they test it at that point, but they never know where the failure is going to be.
Yep.
Yeah, so any rework that's done can potentially back up their order time as well and deliver their product late to the customer, so which isn't good either.
What is their failure rate on this? Do they have a number?
They did not provide us with that number, no.
Well, at that in this case, if that's the way they're doing it, one failure is going to really cost them a lot of time and money.
Right. Because of how fast is developed as a job shop, it could be they get an order and the customer needs it in the next, or if FedEx has one break, they need a new one as soon as they can get it built. If they have an issue, like an electrical issue, and they're spending 40 plus hours trying to rework it, it could really damage their reputation and damage their image with FedEx.
What's the feasibility of using the same type of tool or PLC box in some of their other applications there?
I would say that it is very feasible. The issue with the PLC is that you have to, unless you get kind of complicated with how you're going to do multiple different control panels, you almost have to make one for each control panel you're testing, because generally speaking, when you want to edit the software on a PLC, you have to have a automation engineer come in and reflash the memory, which isn't necessarily the hardest thing in the world, but it's not something a basic operator could just plug a computer in and then redo it. That's kind of why we wanted to go towards the PD450. But as we said, with the whole issue, this coronavirus, we weren't able to test that because that system is a lot more user-friendly, where you can have multiple programs on it at once. So this is just kind of the solution that we had to make do with.
You gave them that other the specs from the other option, did you not?
Yeah, we did. We told them that this is an option, but there's other peripherals that we needed with that PD450, and without us able to get it hands-on or get into contact with the company, we weren't 100% certain that we wanted to fully recommend that just because we had somebody to say it was good. We wanted to be able to see it hands-on before we recommended it fully.
But it sounds like the situation they're in with plenty of these electrical circuit boards or whatever that they potentially could have the test, that they need a fail-safe solution that they can use throughout the plant to test these things as they get moving forward. It sounds like you provided that in a sense, but weren't able to finish that piece of it, so gave them a simplified kind of starting point, I guess, for lack of a better word, to go forward with this PLC.
Yeah.
The main one they wanted us to focus on was a SCISSOR, because that's where they are seeing the most amount of rework, most amount of errors, and most amount of rework. So that was the one they really wanted us to fix. And beyond that, they were if we could develop something, but the biggest one they wanted us to fix was a SCISSOR.
Okay. So have you presented them a solution down there yet? I mean, have you presented this to them yet?
We were unable to schedule a time before today, but we plan on doing that.
Yeah, if you get a chance, that would be kind of nice, so they could ask the similar questions, so that they could continue the research on the off-the-counter, off-the-shelf one if they wanted to, but then they could also do this one as a test to see if it works in their environment, and then go to the next level if they wish to.
Yeah, definitely.
Okay. That's all I have. So if you get a chance, guys, go ahead and publish the recording. Send me the PowerPoint if you haven't already. I don't know if I saw it come across or not yet. And then the final report is due end of day next Friday. And we should be good at that point.
Very good. You mean